Hello, in this lecture we are going to discuss about the measurement techniques in particular which are useful for microchannels and specifically which are relevant for multi-phase flow in microchannels. So because for the flow measurement first we need to think about what are the parameters that we are going to measure. In microchannels, it is often difficult to do point based measurement. For example, what I mean by point based measurement, say in a flow one wants to measure the velocity, then the velocity measurement for say to measure the speed of aircraft is done by say a pitot tube, and pitot tube measures the velocity at one particular point only. Such measurement devices affect the local flow field, and in microchannels it is almost impossible to have such a sensor to measure the velocity at all. Even though these sensors will affect the velocity field, but if we neglect the errors introduced in the velocity field because of such probes, even then the size of the probe itself will be of the micron size, so it is not possible to do such velocity measurements in the microchannels. Okay. So thinking about what are the parameters that one would be interested in measuring in microchannels, and most of these parameters except say pressure measurement, one would be interested to measure these parameters as a whole field measurement. That means one would like to have information of the parameters as detailed as possible. So for example, when we plot the information that we get from computational fluid dynamics, if we are able to get all that information from the measurements, then we can validate our CFD simulations as well as we can use this data to develop accurate models and design efficient devices. So thinking about the equations or the Navier-Stokes equations, we have four equations: the continuity equation as well as the conservation equations, momentum conservation equations, and these four equations are solved to obtain the flow field in a isothermal flow for incompressible fluids. So the unknowns in this are velocity field and pressure field. So those unknowns, if we can measure, while it is not possible to measure while there are very few techniques available which can measure the pressure locally, but recently there are techniques being developed which can measure the pressure locally. But if you look at the literature, there are very few articles available where the local pressure field measurements have been performed. So what we are interested into measuring the velocity field, or the three components of velocity, and the pressure field if possible. If not possible pressure field, then one would like to definitely measure pressure drop or differential pressure between the 2 points. So at the entire channel cross section, because the flow that we are focused about is a multi-phase flow, and in a multi-phase flow, as we have seen throughout the course, the heat transfer, the pressure distribution, the velocity distribution is strongly coupled with the phase distribution, where the gas phase is present and where the liquid phase is present. So based on this, we need an accurate prediction of the phase distribution. So this phase distribution can be in form of flow regimes, which is the first cut information that we would like to have, and then we would also like to know the void fraction or the volume fraction of the phases. Then the temperature field. So if you look at the now we discussed about the velocity and pressure fields, and then for multi-phase flow we also need to know the volume fraction field. Now if the temperature is an important parameter, that means if the flow is non-isothermal, there is heat transfer involved, then we also need to know the temperature field. But as you have seen and as we have also discussed during heat transfer in the Taylor flow regime and during boiling, that the measurement of temperature in the liquid is rarely done. Generally, it is the measurement of the temperature of the wall is performed. It may be by using thermocouples or more recently by using IR cameras. The measurement of the wall temperature is performed. So the wall temperature is obtained easily, but obtaining temperature of the fluid is challenging. There are some experiments have been performed and they are increasingly being performed using LIF, laser induced fluorescence. So where a dye is introduced in the liquid which emits the fluorescence light, or which emits the light whose intensity or the intensity of the light is a function of temperature. So one can measure the temperature of the liquid in such a case. So one also need to know the temperature field, and for mass transfer applications one need to know the concentration field. So again, most of the measurements of concentration are based on the point measurement, that one measure change in concentration, that is concentration at the inlet and outlet, and the distribution of the solute in the channel or local distribution of the species is not known really in such a case. So again, increasingly the use of laser induced fluorescence with suitable dyes is being used, or it is to measure the local concentration field as well. So the temperature field and concentration field, they can also be used by using they can also be measured using laser induced fluorescence. So as most of this discussion, or the velocity field, pressure field, they are coupled with phase distribution in multi-phase flows. So let us discuss about the phase distribution first. Before we do that, here is a typical experimental setup which is used in most of the experiments where there is only adiabatic measurement of the flow. So this is the test section, and in this test section the air, if it is gas liquid flow, the air is supplied from a source, or it might be either from a compressor or from a cylinder, and then the pressure is measured at this point, the flow is measured, and this comes into a mixing device. The water comes through a mass flow meter. The temperature of water is measured and the two phases mix in this mixer. Now in some cases the mixer can be in the test section itself, which is good because then the channel dimensions are not going to change. Okay, so then these mixers, the flow from here comes in and it is passed through the channel cross section, and then the pressure differential using the two pressure sensors are measured, the temperature at the inlet and outlet is measured, and the images of the test section or the flow in the test section is taken using a CCD camera with either a zoom lens or a microscope, because it is not possible to get good enough resolution using just using the camera. So one either need a zoom lens or a microscope to do the task. So for the phase distribution, of course, if one can image the system, then one can get the phase distribution. So for imaging, one needs optical access to the test section. By optical access, I mean the test section should be transparent. So the transparency is required, that the channel should be of a transparent material, as well as the flow should also be, or the fluids, they should also be transparent. For example, if there are a large number of bubbles present in the channel, then the visibility inside the channel will be affected, and it will not be possible to obtain the images of what we will get is the images at the wall of the channel and not at a particular cross section in the channel. So of course this task in microchannels, we require zoom lenses or microscope. When we perform heat transfer experiments, often it is required to supply the heat through the channel wall. So when we supply the heat through the channel wall, it has to be covered by a metallic or electric heater. So the optical access to channel in such cases is restricted, and often the measurements or the optical axis is obtained either making a small section visible in such test section, or looking at the flow field, looking at the imaging the system just downstream the heated section. So these systems are based on the imaging or optical imaging. Then one where optical imaging is not possible, one can also measure the phase distribution based on the properties of the two fluids which have good enough contrast, the properties which are significantly different in the two phases. For example, one can measure the electric impedance of the two phases. That can be the measurement of resistance, the measurement of capacitance, or the measurement of inductance. The most common ones are the measurement of electrical resistance, and it is easier to cheap and build. One just need to put in the wires, and then one can get the cross-sectional averaged resistance of the phases. It is or the other technique is based on the refractive index based measurement. So the refractive index of the phases, if they are different, then with the development in the techniques which can capture very sensitively the variation in the refractive index, then those techniques can be used again to get an estimate of the phase distribution. So when we have optical access to capture the images, we generally need to use cameras, and these cameras need to be very high resolution and high speed camera also. So there are specifically two types of cameras which are used. One is called CCD and another is CMOS, and these names of the cameras are based on the sensors that they used. So CCD camera is based on a charged coupled device, which is in short is called CCD. So the CCD camera converts the light into electric charge based on the photoelectric effect, and the CMOS sensor is also based on the same principle. So in the CCD camera, an array of many individual CCDs or many individual the sensor elements, they are arranged either in a line or in a rectangular array, and then each element is called a pixel. These pixels are charged by the incoming photons. So this charge is transferred through a limited number of output nodes, which is converted to the voltage, and this voltage is sent off as an analog signal to the computer. So the speed of the CCD camera is limited by the number of outputs and through which the signal can be sent. So the frame rates that can be achieved in a CCD camera is limited. However, they have because all the pixels capture the light and the uniformity of the output is high, so they have low signal to noise ratio, and the picture quality that one get using CCD camera is better, especially in the low light. CCD cameras are known to perform better than CMOS ones or CMOS counterparts. But for their manufacturing, a special technique is need to be used, so they are costly. They are costlier than the CMOS counterparts. CMOS cameras, which is complementary metal oxide semiconductors. So they have these semiconductor sensors, and again these semiconductor sensors, they have its own charge to voltage conversion devices. And so each pixel or each sensor has charge to voltage conversion device, and then this sensor itself has a digitization circuit. So there itself the voltage is converted to digital bits. So it is the rate of transfer can be high. However, the sensor size in CMOS cameras is larger than the CCD ones. So a typical CMOS camera will have 20 micron, whereas a CCD camera sensor will be 9 microns. So the sensitivity of to low illumination levels is high, so they might perform poorly, or they perform poorly when you compare with CCD cameras in lower light. However, they can have very high speed, thousands of frames per second, or at low pixel or at low resolution they can even go to up to 500,000 frame rates per second. So most of the high speed applications are based on CMOS cameras, and with the new development in the camera technology these days, the sensors are being developed which combine the good of both the worlds, which can use CCD camera technology for the better resolution, and the CMOS technology for the better or the higher speeds. Okay. So these cameras, they need to be used along with zoom lenses or microscopes. So the simplest microscope that is used is based on Brightfield microscopy. So the Brightfield microscopy is that a light source emits the light from the bottom. So the test section is here, and the light is emitted from the bottom, and it is visualized either through eyes or a camera. So of course, when we want to do the measurements and record it, we need a camera. So the recordings will be done from the other side, and the illumination will be done from the below and observed from above. So this results in the contrast by the attenuation of the transmitted light that is being transmitted through the test section in the dense areas of the sample. So you see a good and contrast image of the sample. Now this will be dependent on, because these are not static images, we have flow happening in this. So we need to look at that the camera should have a sufficiently short camera shutter time. So for those who do not know what the camera shutter time means, it is the time for which a camera sensor is exposed to the light when the picture is being taken, and this determines the exposure time. It will determine the light that will reach the camera. So at high flow velocities, and this exposure time, so when we look at the exposure time, that will be determined by the resolution that we want and the flow velocities that we want to capture. So say for a flow velocity of 0.1 centimeter per second and a spatial resolution of 1 micron, a shutter time of around 0.1 microsecond is needed. Now the illumination that happens is generally using continuous light sources. However, at low shutter times or smaller shutter times, less than 10 microseconds, it is preferred if one have a stroboscopic light source, so that the illumination can be better and the enough light is provided to the camera. Now, so the simplest method for the illumination and the visualization is Brightfield microscopy. However, that is not always good enough to take the pictures or to get the better resolution. So the fluorescence microscopy is often used, and it has a number of applications, specifically with respect to diagnostics in microchannels. One can measure the white fraction distribution, one can measure the flow velocity, one can measure the temperature field, one can measure the concentration field using fluorescence microscopy. So the fluorescence microscopy, in this the sample is illuminated with a light which is often of a specific wavelength. So this light is monochromatic light. This can be done using so say xenon arc lamp or mercury vapor lamp, LEDs or lasers. And this light which is incident on the sample, and this sample is seeded. Sample means the flow, one of the phases of the flow, often the liquid phase or the continuous phase, is seeded with fluorescent particles, or which are called fluorophores. So these fluorophores, they absorb the incident light and then emit the light. Now when they emit the light, the wavelength of the emitted light and the energy of the emitted light is different from the energy the light that is incident. Of course, the energy of the light that is emitted will be lower than the light that is incident. As a result, the wavelength of the emitted light will be higher than the light that was incident. So, the fluorophores, they emit light of a longer wavelength when the light is incident on it, and this light is collected and goes to the detector, which may be a camera. Using a dichroic mirror and emission filters, the illumination light, the light which was being used for illumination, is separated from the fluorescent light, and in epifluorent microscope, this is both the lights which is used for the excitation of fluorophores and detection of fluorescence. Both are done in the same microscope. So, the epifluorescence microscope is where the excitation of fluorophores and the detection of fluorescence both are done in the same instrument. It is called epifluorescence microscope. So, it is basically that the images are taken of the fluorescent particles. So, based on the intensity of that fluorescent particle, one can capture a field, and if this intensity of the emitted wavelength or the emitted light is temperature dependent, then one can measure the temperature field. If it is concentration dependent, then one can measure the concentration field, and if it is not dependent on such parameters, then one can measure the distribution of one phase. So, it is often used, and this technique is also used, or epifluorescent microscopes are also used for micro PIV applications, because the illumination in micro PIV is the volumetric illumination, unlike a general PIV or 2D PIV where the illumination is through a light sheet. So, we have discussed the or we will be discussing the details in a separate lecture about the PIV. Now, this liquid phase can be labeled with either a organic dye or semiconductor nanocrystals, for example CDSE dots, and then one can obtain phase distribution, shape of the interface and concentration fields, etc. For temperature measurement, a dye named as rhodamine B is used, which can be used to measure the temperature field, and this technique is known as laser induced fluorescence or LIF to measure the temperature. For concentration measurement in the liquids, the dye that is used is called rhodamine 6G. In microchannels, the intensity of the light is very small, so one often does not use a continuous light source, but rather a pulsed light source is required. For example, a bubble velocity of about 0.1 meter per second, an exposure time of less than 100 nanosecond is required, so that the resolution is below 10 microns. So, when such high temporal resolution is required, then one need to have a pulsed light source, which are often also used in micro PIV and PIV applications. So, the two common light sources are NdArg and NdYLF solid state lasers, which can have very short pulse duration up to 10 nanoseconds, and they are useful, and the trigger of the pulse is synchronized with the camera. So, we need a synchronizer to synchronize the pulses, that when the camera shutter opens and when the light is triggered from the laser. And the same technique is used in micro PIZ as we have just discussed. So now other technique, till now we have discussed about two microscopes and cameras. So these systems can use the microscope, can image the flow, and from this one can obtain the volume fraction field in the channel. Using a temperature sensitive dye, one can obtain the temperature field. Using a concentration sensitive dye, one can obtain concentration field. Where the optical axis is not there, then there are different other techniques one can use. So one is say based on refractive index based sensor. So as we know that as the light enters from one medium to another, the part of the light is reflected and the part of it is refracted. So what is total internal reflection? So we have, let us say, two mediums. Medium 1 where the refractive index is n1, medium 2 where the refractive index is n2, and the light is incident at an angle theta 1 and it goes out at an angle theta 2. And we know from Snell's law that n1 sine theta 1, where theta 1 is the incident angle and 2 sine theta 2 is the angle of refraction. Now if we keep increasing theta 1, then at one particular angle, let us say theta c, the reflected light, the light will not refract anymore. So if we have this n1 sine theta c is equal to n2. So of course this is true when this is only possible when n1 is greater than n2. So this at this critical angle the light will not refract anymore, and for a higher angle the reflection will be there. So that is what is meant by total internal reflection, that the light does not refract anymore, it reflects. So this is a powerful tool based on which the light can be confined, and the optical fibers and optical fiber probes are also based on this technology or based on this principle, total internal reflection. So one of the techniques that have been developed is that the reflection of laser light at the fluid interface, it can provide the information about the flow characteristics. So in this case, a laser beam enters the channel normal to the flow direction at such an angle that the total reflection, total internal reflection takes place when a gas or liquid which is dispersed in a continuous liquid. So it might be either a gas phase or liquid phase which is dispersed, that when a gas or liquid phase, dispersed phase passes through, and this is dispersed in a continuous liquid phase which has a higher refractive index, is present at the illuminated position. So it is done in such a manner that when the dispersed phase passes through, and the dispersed phase should have a lower refractive index than the continuous phase, and it should come at such an angle, light should come at such an angle that the total internal reflection can take place. So by detecting the emergent beam on the other side of the channel, one can obtain the phase distribution. So when only the continuous phase is present, the beam is almost completely absorbed. There is no nothing happens, and so that the light intensity of emerging beam is very low in such a case, whereas it may not be the case in case of when the liquid passes. So based on the changes in the refractive index, one can obtain the phase distribution. Now another technique which is known as MIBD or Micro-Interferometric Backscatter detection. So in this case, a laser light is used to create high contrast interference fringes, and the shift in fringes is based upon the change in refractive index of the fluids. So because the two fluids will have different refractive indices, so based on the fringe shift, one can measure the change in the refractive indices and change in the properties of the fluid. So the technique, it has been reported, the sensitivity, the technique can detect the changes up to 10 to the power minus 7 of refractive index units. And this technique can be used to measure temperature distribution, concentration and pressure distribution as a function of refractive index. So in this work by Fultz and Allen recently, they have developed a technique to measure the local pressure distribution in a channel by this technique, MIBD technique. So the other technique that can be used apart from imaging and refractive index change is based on the change in the electrical properties of the two fluids, that when one fluid, say gas and liquid, they have very different electrical conductivity or resistivity or electrical capacitance. So if one can have a probe or one can have two wires through which which connect the two ends of the channel, and if this voltage or the resistance is measured, and from this measurement of resistance one can know the change in the phase distribution, or one can know the phase change at one particular location with respect to time. These probes are easy to construct, they are low cost, and if a number of electrodes are used, then with the reconstruction algorithms, one can use these techniques as tomography techniques, where one can determine the entire 2D field at a cross section using tomography. So one can reconstruct the phase distribution at the entire section using a number of probes, which is called tomography technique. So based on this, a number of velocity measurement techniques are also developed for velocity measurements in microchannels. Now, most of the techniques which are used in microchannels for velocity measurement or otherwise are non-intrusive, because as we have discussed at the start of this lecture, it is not possible to do the point measurements in microchannels. So some of the popular techniques are particle image velocimetry and the related technique particle tracking velocimetry, then laser Doppler velocimetry, and MRI or magnetic resonance imaging. Now we will discuss micro PIV or particle image velocimetry in a separate lecture. So there is a brief discussion of laser Doppler velocimetry. In this technique, like micro PIV, it is also non-intrusive, and it measures the instantaneous velocity of a flow field. So one can measure the velocity in space as well as in time, and it can measure all three components. So full 3D velocity with temporal resolution. So it is again a powerful technique, It is based on the, as one can guess from the name, it is based on the Doppler principle, and the wave that is used for it is a monochromatic laser beam. It is sent towards the target, and the light that is reflected is collected, and the change in wavelength of this reflected light is of course a function of the relative velocity between the target object, the relative target object's relative velocity with respect to the source. So, based on the Doppler effect, this relative velocity can be measured, and then velocity is obtained by measuring the change in wavelength of the reflected laser light. This change in wavelength is often measured by interference fringe patterns by superimposing the original and reflected light. So, from that one obtain the delta lambda, and from delta lambda one obtains what is delta V, or the relative velocity. So, that is the principle behind laser Doppler velocimetry. Now, coming to the pressure measurements, the pressure measurements is a difficult bit, but it is very important because it is required to determine the pumping power to run a system. So, it is always required to design a system efficiently. One need to have an idea about the pressure drop that happens in channel. Often pressure transducers which can capture the low changes or small changes in pressure are used, and depending on a particular system one can estimate the range of pressure changes that are that should happen in the channel, and accordingly one should select a pressure transducer for a particular application. It is particularly difficult in to measure pressure changes in microchannels because one is the channel geometry and wall roughness. So, specifically, as we have discussed earlier also, that the roughness of the channels can be an important factor in microchannels because the roughness, which is let us say epsilon over d, the channel characteristic, might be negligible in a small in large diameter channels, but this is something which can be important in large channels. So, the pressure drop is of course will be a function of roughness. So, that is one factor. Then that experimental test rigs that are developed for microchannel applications, if not developed carefully, they are often susceptible to flow oscillations and flow instabilities, and the pressures that are being measured, they are small pressures. So, even a small change or small oscillations in the flow or small instabilities, they can cause errors, large errors in the measurements. And then specifically during the phase changes, the accelerational pressure drop, which is a large component of the pressure drop when the phase change happen because the areas occupied by different phases keep changing along the length. The accelerational pressure drop is an important component of the pressure drop. So, that the different magnitudes of pressure drop components is difficult to obtain in specifically in microchannels because no particular correlations are available which can relate the void fraction with the change in the pressure drops. Apart from that, there are entrance and exit pressure losses which happens in microchannels also, in large diameter or macro channels also. They can be because of expansion or contraction or the flow distribution where the two phases mix. So, pressure drop measurements are generally done using pressure transducers, but one need to take into account all these factors so that the accurate pressure drop measurement can be obtained. Okay. So, with that we can summarize that one of the or the techniques in microchannels are based on where one wants to have the good view of the flow field and the phase distribution, and that is possible using either Brightfield microscopy or fluorescence microscopy. For white fraction measurements, the techniques are being developed based on the electrical impedance changes, total internal reflection, or based on the changes refractive indices. And these techniques have potential to measure the local temperature and pressure distribution also. So with that, we have an overview of flow measurement techniques in microchannels. In another lecture, we will discuss briefly the microparticle image velocimetry technique and its basic principle. Thank you.